Here for problem 8.51, we want to estimate the volumetric flow rate of the saline that can be produced from the needle. So I have a little sketch drawn here on the left-hand side of our system. Now, if we assume that the volumetric flow rate is laminar, we know that the volumetric flow rate Q is going to be equal to pi delta P d to the power of 4 divided by 128 mu L. Now to find delta P, well, we know that that's going to be the pressure at point 1 where we apply the force at the needle minus the pressure at the outside of the needle, which is atmosphere. Here we know that the maximum force exerted on the plunger can be of 7.5 pound-feet. Here we'll assume that that is a difference in force or the difference in pressure, and therefore or delta P will be equal to the force applied, so that's 7.5 pound-feet divided by the area of the plunger. Now, because we're working in British standard units, we have to be careful with the conversion, but we will obtain a delta P of 67.9 psi. The other unknown is the viscosity of the saline solution. In the problem, it is stated that it is 5 times as viscous as water, and therefore the viscosity of the saline solution will be 1.05 times 10 to the minus 4 pound-feet second divided by feet squared. Now that we have solved for all the unknowns, we can retake the expression for our volumetric flow rate and calculate the volumetric flow rate. And again, it's important here to be careful as we're using the British standard units that our feet and our inches all line up together. What we obtain is that our volumetric flow rate is 8.27 times 10 to the minus 7 cubic feet divided by seconds. Now the last step is just to double check that our assumption that the flow is laminar is correct. So here we will just calculate the Reynolds number, knowing now the flow rate. Also, we will assume that the density of our saline solution is similar to that of water. And what we obtain is that our Reynolds number is of 46.7, which is very much a laminar flow.